about the electromagnetic spectrum, of course. Okay, and so we talked about the electromagnetic spectrum. Okay, everything is probably coming back to you now. We talked about the wave, the frequency, the wave and the frequency and the relationship between them. And right here, this equation, okay, which frequency and wave are inversely proportional to each other. And then we talked about, well, we didn't really solve any problem. You might have some in your homework, okay, and that's why the problems are here. So you can always just look up here to get an idea. We talked a little bit about photoelectric effect. We talked about Max Planck and his whole theory about quanta and photons. And then we started with Bohr. We started getting into the atom then. Okay, and we talked about the line spectra. And the line spectra was because of what Bohr said, that if you have an atom, and here is the nucleus, then the electrons will exist in very specific locations where n is equal to 1, n is equal to 2, n is equal to 3. So here there are very specific shells, okay, in an atom. That's how you get the line spectra. So there's nothing in the middle. They're very specific locations. Okay. So we talked about all this, and I think I might have mentioned this a little bit to you about how to calculate energy if an electron jumps from one shell to the other, or it comes from another shell to the previous one. Okay, so it can give off energy or it can absorb energy. So all of the line spectra that you saw in the previous slide, those are not like a suspense. Okay, there's nothing like that. It's not like a melting point or something which you have to go in the lab and find out. You can actually calculate all the line spectra and predict what the line spectra is going to be for any element. Okay, but the interesting thing is that the line spectra is the fingerprint of any element. Okay, so if you want to identify an unknown piece of metal and you want to know what it is, you can just put it in an instrument which is very specific for identifying elements, okay, and it will do it for you. Okay. Now there are about 117 elements on the periodic table, so you can't identify all 117 using the same instrument because all of the line spectra may be in different wavelengths, okay, and frequencies. So you would need different lamps, okay, for it to generate that kind of a frequency. But other than that, if you have 4 or 5 instruments, then you could figure out anything. And this is actually what they do in forensic sciences and also in space science. Okay, if you're going to some other planet or moon or trying to figure out what's in this dust, and then you don't need all of that. You don't need to come in a lab and figure this out. You could just have instrumentation on board, and they will tell you exactly what elements are present on any planet. Anyhow. Going along, this is a little bit more on the calculation on how to calculate the energy, okay, from one level to another level. So this is final, this is initial, this is Rydberg constant, so it's just a constant. And then I think there is an example also given to you. So right here, it's a detailed example as to how to go through calculating the wavelength of the light emitted. Okay, so it did just a little bit of a detailed calculation, but it's very systematic. Okay, there might be a problem in the homework, okay, regarding this. So just look at this problem, see how it's solved, what are the equations that are used, and you should be able to solve this problem. Okay, and that's where we were. Okay, kind of with the transitions. This slide here is just a little bit of an overview, okay, as to what Planck did, what Einstein did, and what Bohr did. Okay, it's just in one slide, that's all. But that's where we were, okay, typically. Now, going on a little bit further into the structure of the atom. So we have this, okay, right here, where you have the Bohr's atom, in which you have the nucleus, and then you have the shells, okay, shell number 1, 2, 3. But then we haven't figured something out yet. There's still something more to be figured out. Should I give you a minute to think about this? 30 seconds or something? Raise your hand if the question comes to your mind. Just wanting to see if it comes to your mind as to what is missing. What do we still need to know? over here? We know that there are shells here, right? We know there are electrons in these specific locations, but what else do we need to know? How many electrons, okay, in each of those shells, okay, that we have. So if we have shell number 1, does it have 5 electrons? Does it have 6 electrons? Okay, and then shell number 2, how many does it have? Okay, things like that. So that's also something that we need to know. Okay, the other thing is, fine, we have an electron. We have an electron here. Okay, that's been established. Okay, it's not over here, it's on the shell. But if it is over here, is it over here? Or is it over here? Or is it here? Do you see what I mean? So what I'm trying to say is the electron in motion, okay? And it technically is in motion, okay? So an electron is in motion, and this was established by Louis de Broglie, and he established the whole wavelength thing here, okay? And what that means is that the electron is in motion, but not just in motion as in motion. It is actually going around in a waveform. Okay, so just like the light is traveling in a waveform, the electron is also traveling in a waveform. Okay, and so that's how it is going to be in motion. And so, let me try this again, see if I can get this right. So if an electron is going around like this, it's going to go around in a very specific, and my course drawing is beautiful. It's going around in a very specific wavelength. Now, when you're trying to complete this wave over here, when you draw this in circle, okay, you will see that sometimes it may not complete the circle. So for example, it can be like this. Do you see that? Do you see the small difference there? So maybe it started from here, but I'm ending here. Does that complete the wavelength? It doesn't really complete the wave. Okay, so which means that the wavelength has to be very specific because the wave has to be complete. Okay, and that's what the calculations are for. Okay, to make sure that you have a wave in there that is a complete circle. Okay, that goes around. So which means that the wave that you have here may not be the wave that you have here. Okay, the wave here could be a little bit larger, but even if it is larger, you still have to complete it. Okay, all right, you still have to complete it. So that's what de Broglie established, okay, in his theory, that you have this kind of a wavelength thing. And then with Erwin Schrödinger, both of them, okay, they kind of worked on this. And the whole wave property, okay, the whole wave property of the electron is now used in an instrument which is called the electron microscope. And I don't know if you've heard of it. Nod, shake, yes, nod, you've heard of it. Electron microscope is a great tool, so you can really see in depth, okay, into inside, you know, cells and whatnot. And so the electron microscope could be devised only because electrons have a wavelength. So what they do is they tune into that wavelength, okay, and then they project the images. So that's how the electron microscope is used. But that's what Louis de Broglie and Schrödinger established. Okay, so fine, we have the wavelengths going on for us, okay. And then comes in Heisenberg, okay, the last scientist's name over here. And Heisenberg says, okay, well, in that case, you should not be able to tell the location of an electron, okay? Because if an electron is traveling in a waveform like this, so whether it's traveling or whether it's in motion, and whether it's in a wave motion or not, it doesn't matter. But if it is going around, you cannot tell the location of an electron, okay? And so the best example I can give you of this is if you're sitting at a racetrack and watching cars zoom by, you can only either look at a car or you can look at the track, right? You can't look at both the things. If I were to start doing the pendulum here for you, walking around like this all the time, you can't look at the board and me at the same time, okay? It's not going to work. So you're either going to look at the board or you're going to look at me, okay? And so that's what he said. So Heisenberg's principle says that you really cannot pinpoint a position of an electron and say, here it is. Okay, so you can't say that. So that's an interesting point also, because nobody has been able to establish that either. Okay, which means that all we can say is there is a general location of an electron, and this is where you will find it, and that is called the wave function. So if an electron travels in a wave, okay, then these are the locations where you can find an electron, right here, and over here. Okay, and these curves, they're known as psi, which is this symbol. That is psi, psi. And so the probability of finding an electron in a wave is given by psi square. Okay, this psi is positive psi, and this one down here is a negative psi, only because of the graph, not because of absence or presence of electron, but because of the graphical nature of a wave. Okay, but otherwise this is a positive region, this is a positive region, or place where you can find an electron. This place right here is called the node, and you cannot find an electron in the node. Okay, you will never find an electron there. So for example, as you are sitting on a chair, we'll find you here, we'll find you on the chair there, we will never find you sitting on the aisle, at least not here, maybe in India, but not here. Okay, and so that's the probability of finding you in a location. Okay, so that's exactly what we have for this. Now this part over here, which I've shown just in a very small region over here, it's a very small part that we learn here, but you're going to learn that again in GenChem 2. You probably will hear of it again in organic. Okay, this is an important part when bonding comes along also. Okay, and so you will hear about this again. So the wave function, okay, wave function is the psi. And psi square is the probability of finding an electron. Okay. That's what this is about, and I think that's pretty much the end of this over here. Yeah.
Dr. Krishna?
Yes.
How, like, what keeps, like, the shells in their place around the nucleus?
It doesn't. There is nothing. And I was going to say in the next chapter, but I can say it now also if you want me to. But the way I think about electrons, first of all, okay, is not as an object, like a pinpoint object. Okay, I think of electrons as clouds, as density of negative stuff. Okay, that's one thing. So that's why we can say the general location is here or here. Okay, I can't go and say, okay, I got an electron. Okay, so that's a hard thing to do. So if you think of an electron that way, it would be easy. Okay, the second thing about the motion, and I think that's what your question is how is it staying over here? Is that what you're
how
asking?
is it staying in that ring? How is that ring even staying?
How that ring stays there, it is, there are different forces involved. Okay, and again, if you think of the planetary model, okay, that makes it a lot easier. Okay, that's what I was asking last time. Is there a highway on which the Earth is traveling? No, there isn't. Okay, it's the gravitational pull of the sun that's keeping everything. Okay, and if we get out of orbit, we'll be dead. Yeah? That's exactly what the force is holding the electron also. You're right. Okay? And these shells, they don't move. They're in very particular locations. Okay? Yeah, just like that. So it's a very, it's a force. And I think you do that a lot more when you get to quantum chemistry. Okay? All right. Any other questions? We're good? Okay, that's just the basics, okay, of how and where the electron can be found, but we're not quite done yet, okay, because now we'll go into what we call the quantum numbers, okay, and quantum numbers are pretty fun to deal with. Okay, so today this is what I'll be working on, okay, and so if you have your PowerPoints, you can just write it on it, you know, and then this is the diagram I'll be drawing out for you right here. So all of these things, it's all there, but I still would like to draw it for you, okay, so that you understand how I'm getting all of these things here. Okay. Quantum numbers are actually quite fun, okay, in a way. I really like quantum numbers just because they're so abstract, okay, in a way. Quantum numbers give us an idea of the location of where the electrons are and how they can be found, what shapes they would be, if there's any shape, the whole wave function thing, okay, that gives an idea of how they're located. So that's what quantum numbers really are. So it's all about what is possible and what is not possible. Okay, so quantum numbers. And there are 4 quantum numbers, and we'll start with the principal quantum number. And I will not write quantum again because that's too much work for me. Okay, and that is called n. Principal quantum number is called n. What I will do, of course, I'll write over here and I'll draw a diagram here so you can see how it works as far as an atom is concerned. So I usually go up to 4 because that's the best thing to do, and if you have color-coded pens today, it will really work well for you. Okay, so the principal quantum number, which is n, okay, n is never going to be equal to 0, okay? So n will start from 1, 2, 3, 4, and so on and so forth, okay? And again, no fractions also, okay? Only whole numbers, and it's not 0, okay, as well. So that's the number you've already learned as far as board was concerned. So n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. And that's the principal quantum number. Okay, and there it gives you an idea of where you can find the electron. Shell number 1, shell number 2, shell number 3. Okay, the next one is angular momentum. And this is designated as L. As you work through these numbers, they are worked from the number before. Okay, so which means that I will work for the number L from n. Okay, so L is 0 and then n minus 1. N is equal to 1, n minus 1, and so on. Which means that L can have multiple numbers. Okay, what does that mean for us? And this is a good time to have a new color. So, if n is equal to 1, now remember n can never be 0. Okay, and that's what we mean by allowed numbers. Okay, and not allowed numbers. So n is not allowed to be 0. The smallest number possible is 1. Okay, so if n is equal to 0, then L is equal to, sorry, if n is equal to 1, L is equal to 1 minus 1, which is 0. Okay, all right. If n is equal to 2, then L is equal to 2 minus 1. So it's not just going to be 1, but it's going to be 1 and 0. Okay, hence the 0 over here. And all the numbers, subtraction, okay, after that. So n is equal to 3, then L is equal to 3 minus 1, which is equal to 2, 1, and 0. So there are 3 numbers possible if n is equal to 3. If n is equal to 4, then L is 4 minus 1. That is equal to 3, 2, 1, and 0. How does that work? On the shell, this is how it works. Okay, because all these numbers are all well and fine, but unless you see how it works in an atom, that's not going to make any sense. So right here it says n is equal to 1. So which means that L is equal to 0 at this point. If n is equal to 2, L is equal to 0 and 1. Good. And then if n is equal to 3, L is equal to 2, 1, 0. Okay, that's what it means. And then here L is equal to 3, 2, 1, and 0. Yes.
And we always write the numbers down like
No, no, no. I'm writing it because I need to write more on there. Okay, but you can write them horizontally also. Okay, as you wish. Yeah.
L is equal to 1 or L is equal to 0 on the second shell?
On the second shell, 0 and 1. So it can have 2 numbers. Okay? Yeah, n is capable of having only 1 number, but L is capable of having more. Okay? And so then here L is 3 values and L is 4 values, and then we don't have more than 4 values yet. Okay, for L. You can have more, but they haven't come up with more yet. Okay, which I'll tell in a minute. So right here, when you get into the L numbers, then there is a little bit of a confusion, because when I say 1, okay, that 1 can belong to L, or that 1 can belong to N also, right? So the 1 number then gets confusing. That's what you have when you have so many numbers. So which means what we end up doing then is giving these numbers letters, okay, alphabets. So 0 for us becomes S, So right here, 0 is still S, 0 here is still S, 0 here is still S. 1 is P, and you don't have to give brackets if you don't want to. I was just writing that, but it doesn't matter. P and then P. 1 is still P, 2 is D, and then 3 is F. So then we have these 4 letters that go with those numbers, which you will see will make life a lot easier because you're not talking numbers all the time then, okay? Because then you know exactly what you're saying, all right? So what we're saying then is that when n is equal to 1, L is equal to 0, which means I'm talking about when L is S, okay? And here it is S and P. Here it is, I'm going backward here. What did I do? Okay, no big deal. If you don't mind, I'm going to go ahead and change this. 0, 1, 2, 0, 1, 2, 3. I don't know how I wrote that opposite. Okay. No big deal. There. And so then this is S, P, D. This is S, P, D. And then 3 is F. The ends, they're called shells. The SPDF, these are called subshells. Okay, they're also called orbitals because these are orbits. So there are different names that you can use for this. So N, orbits, shells, whatever you want to call it. Okay, that will work. And then the angular momentum, the L, these are called subshells. Or orbitals. I tend to call them orbitals a lot more than subshells. Good? So far? Okay. The next number that we have is going to be the magnetic quantum number. And the magnetic quantum number is given by ML. This is a small m, and this is a small l, but the L is even subscript, okay, of that small m. So it's a small m and a small l. So the magnetic quantum number is going to come from L, okay, and then ML is equal to 0 and then plus minus L. What does that mean? It means, get a different color first of all, then if L is equal to 0, then ML is equal to 0 as well. That's the only thing possible. 0 is 0. If L is equal to 1, then ML goes all the way from -1, 0 to +1. So it's the full range. Okay, that's why it's the 0 and then plus and minus L. So all the way, okay, in there. When L is equal to 2, then ML is from -2 all the way to +2. So -1, 0, +1, +2. When L is equal to 3, ML is -3, 2, 1, 0. So what does that mean for us? Right here. Here we have L is equal to 0, which means that ML is also 0. When you're looking at shell number 2, now shell number 2 has 0 as well as 1, okay, which means that the ML here is 0 for that 0 number, and for 1 it's going to be -1, 0, and +1.
So ML could be four numbers.
In this case, there are 4. Yeah. But the way I want you to look at it is not as 4 numbers, but then it derives it from 0. Okay, from L number. Don't think of it as 4. Yeah. And then here, ML is 0. For 1, it's going to be -1, 0, +1. And for 2 is going to be all the way from -2 to +2. You get the gist, right? Because I'm running out of room, obviously. Okay. Good so far? All right. What these numbers are is they tell us what is allowed and what is not allowed. Okay? Let me give you an example. Okay, right here. So if we say n is equal to 1, L is equal to 0, ML is equal to +1. Is that an allowed format of numbers? No? No. Okay, then why? What's not right here?
Because ML can only be equal to 0 when L is equal to 0.
Okay, and that's what it means, okay, with the allowed numbers and the not allowed numbers. So you look at the first one first, okay? The n number always is right, okay? The n number cannot be wrong unless, of course, I write n 1.5, okay? Then obviously n is wrong, okay? Because n cannot be 0 or fraction. But otherwise, you start from n, see if L is valid. If L is valid, then you go on to the next one. So yes, obviously this was not valid, okay? So this is not allowed number. And at this point, okay, the whole point is for you to learn what is allowed and what is not allowed, okay, with these calculations. Good? Okay. All right. What do these things mean here? Okay, what do these things mean with all these plus and minuses? These plus and minuses, these are even further down and deeper, okay, than the subshells or orbitals. So these are called suborbitals, which means that L, which is 0, has only 1 suborbital. L, which is 1, has 3. L2 has 5. And then L3 has 7. What does L mean here? L is for SPDF, right? That's what it means. So S has 1 suborbital, P has 3, D has 5, and then F has 7. Okay, suborbitals.
So when you're working with like, in basic chemistry, like high school chemistry, you're taught that there's a certain amount of electrons in each shell. Is that where this?
That's where this is going. Okay, yeah, that's exactly where we're going. But how do you figure that out? You know, so that's what this comes in. Okay, and by the way, I should not say that all of this work is easy. It's not easy. This is all very theoretical. A lot of it is calculation work, okay, and it's very theoretical, very abstract work. And very sadly, I have to say, even though I love quantum numbers so much, you will never see the quantum numbers again until you get to quantum chemistry, okay? So you will see the SPDF, okay, those orbitals you will see, but you will not see the quantum numbers as we are writing them. You will be referred to as, okay, we have the shell number, so you know we're talking about the principal quantum number, okay? We'll talk about S, so you know you're talking about angular momentum, but you will never be referred to as that, you know? So there's a certain sense of loss, like I learned all of this and now what? Nothing, you know? Sorry, okay? Yeah, there are things like that too. Okay, so S here means that there's only 1 suborbital. P here means there are 3, D means 5, and F means that there are 7, okay? What does this really mean for us? It means that S can have only 1 shape. So what the magnetic quantum number is doing for us is actually giving us the shape of orbital. The shape of the orbital meaning where you can find the electron, okay? Not that the electron is shaped that way, okay? Remember what I just said a few minutes ago? That if you think of an electron as a cloud, then it's a lot easier. It can exist like this, it can exist in this shape, okay? Or I should say it can exist in this space, not shape. So this gives an idea of where you can find these electrons, okay? So the shape of the orbital for S is going to be spherical. I'm going to give a different color. is dumbbell, and D is complex, and F is super complex. I'll show you what that means in a minute. Those are not actual shapes, by the way. You probably figured that out. So S is spherical, and please think in 3D. Okay, don't think 2D. Okay, when you have atoms are in a 3D. Okay, otherwise we would be 2D, which I'll be happy with 2D. That's fine. But they are all 3D. So when we say spherical, we're not saying that it's just cut out of paper spherical. We're talking about a ball spherical. Okay, so it's spherical in shape. So which means that you have this soccer type ball or basketball, whatever ball type you have, and that's where you find the electron. Okay, in there. In a dumbbell shape, this is what you have. Okay, and so these are the regions where you find the electron. Okay, and the node is in the middle then. Okay, that's where you don't find an electron. So this gives us a general region of where you can find the electron. This was the wave function that I was talking to you about. Okay, it gives you an idea, okay, of where the electrons will be located. But we still haven't come to the point as to how many electrons are we talking about. Okay, so each of these suborbitals, each of them can handle 2 electrons. So this can handle 2 electrons. Each of these can handle 2 electrons each. So which means that the total number of electrons in P is going to be 6. Just add them up. Total of 6 electrons. The total number of electrons for D is going to be simple math. And for F, it's going to be 1, 2, 3, 4, 5, 6, 7 times 14 electrons. So S can handle 2 electrons, P can handle a total of 6 electrons, D can handle 10, and then F can handle 14 electrons. Okay? All right. Let's go on over here now.
Where does the 2 come from? Where does the 2 electrons come from? Is that just
No, that's just how many electrons this can hold. One suborbital can hold.
different in every problem, or just in general, those 2 electrons?
It's always going to be like this.
Okay.
Yeah, and it's a calculated fact, and it's known that it can handle 2 electrons. Okay. All right. So which means that now I'm going to take this chart and I'm going to write all the electrons. What happened? Are we good?
Yeah.
Yeah, it was just conflicted with something from biology class.
Oh, tell me
A
what.
max of 8
It's always fun.
electrons.
Oh no,
Yeah.
that's fine. That's okay. We're getting there.
Oh, okay,
It's
we're not
okay.
there yet.
We're not there yet. No. There's no conflict. No. Sciences don't conflict. We complement. Okay.
What just happened?
So if you look at shell number 1, shell number 1 has L is equal to 0, which has the s orbital, okay, where ML is 0, 0 meaning only one shape possible, okay, and only 2 electrons possible, okay, over here. When you look at L is equal to 2, you have L is equal to 0 and 1. Here ML is 0, and then for L is equal to 1, you have 3 shapes, which means that S can handle 2 electrons, P can handle 6 electrons. Yeah, feel free to talk. And so which means that the total number of electrons possible are 8 electrons. Okay, here you have 2 electrons, P again can handle 6 electrons, D can handle 10 electrons, so we have a total of 18 electrons. Okay, so then the 4th shell, which has so many orbitals now in there, or subshells, then it can hold it up to, I think it can go up to 32 electrons. Okay, good. The formula for finding out, if I were to ask you how many electrons can shell number 7 hold, you can do 2n squared. That's how you figure out, okay, how many electrons any shell can hold. So the first shell, where n is equal to 1, so if n is equal to 1, then 2 times 1 square, that's 2 electrons. So for 7, 2 times 7 squared, that's 2 times 49, 18, 1, fantastic, 98 electrons. And that's just the 7th shell. Okay, and how many elements do we have? We have about 117 or 114 elements, which means we only have 114 electrons to fill, right? That's all we have. So that's why we don't need more shells than that, right? But anyhow, we'll see as we go on how these things are filled out. But that's the formula you can use to figure out randomly how many electrons, okay, you can fill out. So far, so good? Yes? Okay. Essentially, what we're trying to do with the quantum numbers is also get the address of an electron, okay? So when I say that I'm talking about this specific electron, you and I should be on the same page, okay? So when I say I'm talking about a 3n electron, then you know it's in the third shell. If I say I'm talking about 3s, then you know it's in the s orbital, okay? But then there's still something missing because s can actually hold 2 electrons. So which electron am I talking about? We still have a confusion, okay? For that, we have the last quantum number, which is called the magnetic spin number. And magnetic spin number is given by ms, again a small m and a small s. S is again subscript. This is the easiest number you will find because it has only 2 values, plus half and minus half. It does not come from any of the numbers before. It is independent of this, okay, of anything else. So when you have 2 electrons in one subshell like S, one of them is going to be plus half, the other one is going to be negative half, okay? How does that work and what does it really mean? Well, I asked you to think about the atom as a planetary model, okay, in which case the sun is in the middle and the planets are all around, okay? So the same thing goes for the atom. You have the nucleus in the middle and you have the electrons going around. So just like any planet, just like Earth, and think of Earth because this is where we live, is think about the 2 motions that we have, okay? One of the motions is around the sun, correct? And that gives us the day, the year, the week. What does it give us?
Calendar.
1 year around the sun, right? Okay, so 1 year around the sun, that's what it gives us. The second motion that the Earth has is on its own axis, right? And that gives us the day. Okay, so we have 2 motions that we study. And then we also know that the Earth has 2 poles, right? South and a north pole. Okay, and so, which means that the Earth is magnetized. All right, so it's spinning like this and it's also spinning like this. It's exactly the same motion that the electron has. Okay, so it's spinning on itself also and it's going around the nucleus as well in a wave motion. It would be so interesting to go and see inside. If I was that small and just go inside and look at the electrons, it would be so much fun. Okay, but they're moving like this all the time and being in motion. Okay, it would be so interesting. But anyhow, so if each electron has a magnetic field, and if you have a north pole and a south pole, then we know, please tell me you've all played with magnets at some point, and you know that north will repel north, right? Okay, so which means that you have to have things in opposite spin in order for things to exist properly. Okay, that's how it occurs. So one is plus half, the other one is negative half. Okay, that's all there is to it. It doesn't mean this does not exist. The north and the north pole can exist. It's just very high in energy. Okay, and we can get things to spin. We do. Okay, and we'll talk about it in the next few chapters. At some point, I think it will come up. But you can get the atom excited enough that the electron flips, okay, to get the same spin. And once it does, it's just very high in energy, and then it will come down eventually, okay, to its normal flip. Okay, that's what these 2 numbers really are. So which means that if I were to write the ms number here, it would be plus half and minus half. Okay, the ms for here is going to be hard for me to write because it's for each of the electrons, so there's no point writing all of that out. Okay, good so far? All right. So then, Is this correct? Is this possible? Do you think?
I don't think so, because the ML, I don't think it goes in the.
You don't think ML is right?
Minus 1.
Okay, so ML has to relate to L. It can't be more than that. Okay, so that number is wrong. Okay, fine, I will change that. I will make it +1. So all good now? Okay.
How do we know if it's good or not? Because we don't know what MS is. Like,
It doesn't matter. It's an allowed value, right? That's all I'm asking. Are these numbers allowed? Okay, that's all it is, which means that are they valid? Are they logically possible? Yes, they are. Okay, yeah. Which electron I'm talking about, we're not talking about that yet, okay? Yeah, yes.
So, I mean, L can't be negative, right? So if L was -1, then ML would have to be -1, is that?
But as you said, L
But
can't
L
be
can't
negative.
be negative.
Right. So if I were to write this, then you would say, no, this is wrong right away. So you will not even bother to go here.
Yeah. So where would you use the -1/2? Or how would that, what would that one
What
be?
do you mean the -1/2?
Well, you said it can either be, MS could either be +1/2 or -1/2.
So I can put that to be -1/2. All that is saying is that my spin is either this way or my spin is this way. That's all it's saying.
Okay.
Okay? Yeah. So it just tells the direction in which the electron is. Which direction, it doesn't really matter. So plus doesn't necessarily mean the electron is pointing up. There's no up or down. There's north and south. Okay, so I'm not even saying that, which one is which.
so
Yeah.
the only time NMS will be wrong is if it's not 1/2.
If it's 3/4, for
Yeah, if it's
example.
anything that
Yeah,
isn't 1/2.
exactly.
Okay.
That's when it's going to be wrong. All right. So now when you look at this, how many electrons am I talking about?
You're just talking about one, right?
Am I just talking about
Yeah,
one?
yeah,
Because.
You're identifying just the one,
Because.
because you have an MS number there.
That's it. Okay, so if I give you an MS number of -1/2 or +1/2, I'm just talking about a single electron then. Okay, so don't look at N over there. If I have this here, that means I'm just talking about one electron. Okay, where is that one electron? That electron exists in shell number 2. So that electron is in shell number 2 in a p orbital. Okay, which one it is in? It's in +1 and it has a minus spin. Okay, that's what I'm talking about. That's the address of that electron. Okay, are we good? Okay,
The other electron in that would be +1.
would be +1/2 then.
Yeah.
Yeah, yeah.
For ML, you just have it as +1. When you say that it can be -1, 0, +1, it just has the potential.
It has the potential, exactly. So all the three numbers are valid. Yeah. All right, so far so good? Now, if I were to remove this number from here, then how many electrons am I talking about?
2.
2. Now I'm talking about 2 electrons. Okay, because as soon as I say ML is +1, then +1, this can hold up to 2 electrons now. Okay, so that's how you determine how many electrons we're talking about. Okay, and the location of the electron so far. Yes, Samara.
So if you took away ML, we would be talking about 6 electrons?
Exactly. There you go. Because at that point, if I take away this, I have the possibility of having 6 electrons, but I could also have 0, which is also a valid number for L, and then I'll be talking about 2 electrons. Yeah. Okay. So those are the kind of questions you get also, by the way. Okay, when you start doing quantum numbers, these are the questions you'll get. Are these set of values valid or not? How many electrons are we talking about? What is the location of this electron? Which means that does the electron exist in L or S? So like right now, we are talking about S electrons. Are we good? Yes? And if I were to change that to 1, we're talking about P electrons now. Okay, which means we've changed the wave function of the electron. That's what we did. We went from spherical to dumbbell shape. Okay, that's what we did. Yes, Samara, last question.
The wave function of L or of S in N1 would be the same as the wave function of S in.
Absolutely. So the shape does not change.
Okay.
Okay? What will change is the size.
Okay.
Okay, because now we're getting into larger. Okay, which also gives me a good segue to get into my next stuff, which is size and energy. Okay, yeah. So good point there. As we go outer to the larger number of N, okay, you're getting bigger and bigger in size, okay, because the shell number is increasing, so which means all the orbitals, the S, P, D, F, they will also increase in size. They will have the same shape, but they will increase in size. Okay, that's one thing. More importantly, okay, and this is something that we need to write down, is the energy. Okay, because the energy is very important when we're trying to fill out the electrons in them. So for N, okay, if you have a different color pen, which I'm running out, I don't have a green one today, is if you have N, 1, 2, 3, 4, this is how the energy increases. Okay, so 1 is lower in energy, 2 is higher, 3 is higher, and so on and so forth. Okay, so energy increases this way. When you have L numbers, which is 0, 1, 2, 3, and so on, energy increases with number also. Okay, so which means 0 is lowest in energy, and 3, which is F, is highest in energy. S is the lowest in energy. So which means that when the electrons are filling in to these shells, they will go to S first, and then they will go into P, and then they'll go to D, and so on and so forth, okay? Later on, we're going to have some exceptions also, which I know we all hate exceptions, but we gotta live with them, okay? So we'll have those as well. Okay, regarding these ones over here, okay, because in this case, here you have ml is equal to 0, so you only have one shape, so nothing is possible in this one, okay? But where ml is 3 different shapes, minus and 0 and then plus, then which one has higher energy? Neither of them does. They're all equal in energy, okay? So they are all equal, which means you can fill any of them first, no problem, okay? The same thing goes with all of these. They are also equal, and these are also all equal. There is another word for it, okay, which is called degenerate. And this means equal energy. You might see it somewhere, that's why I'm writing it for you, okay? I don't tend to use this word that much, okay, but degenerate means that something is equal in energy, okay? So when you're filling in the p orbitals, you can fill +1, 0, whichever one you want first, okay? It doesn't really matter because they're all equal in energy. The magnetic spins have no energy, okay, as far as that is concerned. Are we good so far? Okay, let me show you some pictures because pictures do so much more justice than what I'm talking about. When I say a ball, you're like, okay, this is just a ball. But let me show you some shapes of some of the orbitals, the complex ones. The complex and then the more complex one. Anything. All right. So let me go back here. These are the quantum numbers that we were talking about then. So this is a very nice comprehensive sheet, okay, that we have. This table, I don't know if it's from your textbook or not. Probably not because it says 6 and I think we're on 7. So we're on some other textbook here. But this is a good table as well. It gives you all the possible numbers, okay, in there. So these are called allowed numbers. And then here are your 4 quantum numbers that are possible. This goes through exactly what I was going through with you. Are these numbers allowed or not? Okay, so go through this so you can see what numbers are allowed and what are not. And then here's the pictorial of what I was doing with you, okay, on the board there. So this is exactly the same thing. This is a little bit more. It doesn't have the MS numbers in there, okay, but it does have the total number of electrons and so on and so forth. Okay, and then here's another view of it, okay, of what it might look like. It just depends, okay, of what works for you, okay, and then here's another problem set. So the top one there, is that allowed?
No.
No?
No.
Yes?
No.
Okay, no. Which number is wrong?
L.
L number. It should be less than 4. Okay, it can be anything less than 4. Okay, so that's how this one works. Without looking at the answers, go through everything first, okay? Although it's hard when you print out the PowerPoint, right? But you can just fold it, okay, if you want to. So anyhow, the shapes is really what I wanted to show you. So this is the shape of the orbital. So here's the s orbital again. Think of it like the Earth or ball, whatever it is. And the size increases, so one s, which means the s in one shell, is smaller than the s that you will have in the second one because all of them have s's in them. Okay, so Each of them will keep increasing in size as you go out to the shell. The lines that you see over here, okay, inside here, these lines have to do with the wave function. Remember the psi that I was talking about, the positive psi and the negative psi. So we have two electrons. Those two electrons have to coexist, okay, in the subshell. So one of them is going to be in the positive region, the other one is going to be in the negative region, okay? And the middle part, where you have this very fine line, kind of, that's where the node is, which means that you will never find an electron there, okay? It's easier to see when we go into the p orbital because p is dumbbell shaped. So in a dumbbell shape, it's a lot easier to see. Now this dumbbell shape, this is going in 3 different directions, okay? So remember we have the -1, 0, and +1, okay, for p orbitals. So the dumbbell shape is going vertical, horizontal, and then out of the plane, okay? So there are 3 shapes for this, or 3 directions for this. And that's what this shows over here. So we just call them X, Y, Z. So PX, PY, PZ, okay, they're the 3 orientations for the P. When you draw them all together, they come out as a beautiful flower. There. Not my beautiful flower, but anyhow. And that's a total of 6 electrons, which means that each of these is holding 2 electrons, 1 here, 1 here. Okay, and then here is the node right in the middle. Here are the 2 dumbbells here, so 1 electron here. So there are a total of 1, 2, 3, 4, 5, 6. Okay, 6 places where the electrons can exist. Okay, in each of these subshells, they have their psi positive and psi negative region. Whichever it is, it doesn't matter. Okay, for us. But that's what P looks like. D gets more complicated. Okay, now remember D, you will not find D in shell number 1 because for D to exist, you have to have L is equal to 2. Are we good? Yes. L has to be 2 in order for D to exist. Okay, and L cannot be 2 in either shell number 1 or shell number 2. Okay, so there's no D there. We're starting with D in the 3rd shell, so the size will increase, and of course you have more shapes because now we need to accommodate more electrons. Okay, and then we need to accommodate 10 electrons in there. So these are the possible shapes. Okay, for all of these, you get a little bit more idea of these shapes when you get to inorganic chemistry, not even physical. This is more inorganic and quantum chemistry. Okay, and so that's where you learn a little bit more about all of these different shapes and how it plays a part in the bonding. I don't do too much. I will deal with S and P. Okay, so I really need you to know the S and P. And if you're going on to organic, then you definitely need the S and the P. Okay, D we talk about very little bit. Okay, not too much. Okay, so those are the D shapes. If you don't remember the shapes of D, that's fine. I will not be hurt. And F is super fantastic, and I just love this slide because of the colors, I think. The reference is right there. If you click on it, it will take you to the website. But this was one of the best drawings I found. They're really super complicated, where you have all these rings and nice bubbles going on everywhere. Okay, but these are 7 different shapes where electrons can actually exist. Okay, if you are thinking electrons exist like this, please don't think like that. Okay, they don't. Okay, those are the region in which they exist. That's how you should think of it. Okay, those are the regions where you can find an electron that is not the shape of the electron. Okay, please think of that because that's a very important thing to know. So right here, these are the different regions. But anyhow, that's what these different shapes are, and here's all the shapes in one slide there for you. So you can see how it goes from being very simple to ultra complex. Okay, shapes when you start having larger quantum numbers. Okay, so that's essentially is what quantum numbers are all about. It's trying to figure out how many electrons go in which shells and in what orbitals, okay, and what not. So I have a little assignment for you which you can help me out on. Okay, actually you can help yourself out too. That would be good. Because the next task that we have, this chapter is over. Okay, chapter 7 is done with. So in the next chapter, what we will do is electronic configuration. Electronic configuration is now using these quantum numbers to fill electrons out. Okay, so in this one, you just learn about what is a valid number, what is not a valid number. Where do those S, P, D, F come from? What does it really mean? Okay, where are they coming from? That's where they're coming from. Okay, and again, remember, those very theoretical. It's very abstract calculations, but it is established. Okay, that this is how it exists. So the next task is to take an element and start filling electrons, okay, in these subshells. So those things that we talked about over here about what is equal in energy and what is lower in energy is what's going to play a role, because that's how you fill electrons in. Okay, so for example, if you're filling in for hydrogen, hydrogen has only one electron. Which shell will it go in? Shell number 1. Okay, because that's the lowest in energy. So you start with the lowest in energy. Okay, in shell number 1, what is the subshell you have? Only S, right? So only S. So you can put that only in S. All right.